So in the third part of this presentation about inference for two samples, what we're going to do is we are going to look at uh, matched samples, otherwise known as paired samples. Okay. Now, here's an example. A Chicago-based firm has documents which must be quickly distributed to district offices throughout the U.S. The firm must decide between two delivery services, UPX and Intex, to transport its documents. So, in testing the delivery times of the two services, this firm sent two reports to a random sample of its district offices. One carried with UPX and the other with Intex. Okay, so it's doing a little experiment here. So it's picking out a few offices and seeing which of the two companies gets there quicker on average. Okay, do the data on the next slide indicate the a difference in mean delivery times for the two services? Use a significance level of 0.05. Okay, so that's our, there's our alpha of, just get rid of that. There is an alpha value there of 0.05 alpha. Okay, so here is, so it sent a document to Chicago, or from Chicago to Seattle. With UPX, it got there in 32 hours, and with Intex, it got there in 25 hours. Likewise to LA, 30 with UPX, and Intex 24. So what we have here is a sample of, it just took a sample of these offices. Now an important thing to be mindful of is of how many offices are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 offices. Okay. Now, the second thing we're going to do is compute the differences here. Now I've actually have it all done out here. But essentially, what we're going to do is pick a direction, so or pick a sort of little formula for computing the differences, and in each time we are going to use the exact same formula no matter what. So UPX minus Intex, 32 minus 25, that gives us 7. 30 and 24, 30 minus 24 gives us 6, and so on. The thing about the direction is relevant here when we get to places like Atlanta. 14 minus 15 gives us an average or a difference of -1. So just be careful about that. Keep your directions consistent, as in keep the formula consistent with every other. So um, you should get minus the odd. Will get minus sign. Minuses the odd time. Something that people do is go 15 minus 14. The difference there is 1. Keep the directions consistent with all the others. UPX minus Intex. Okay. So what we're going to do then is we're going to look at these differences here. We're going to call these differences, but actually, just for the sake of clarity, I call them case-wise differences quite often. And it's just to be very clear about what type of difference it is, with the cases being 1 to 10. So the difference for case 1 is 7, the difference for case 7 is -1, and so on. Okay, so what we're going to do is develop an hypothesis here, and the average, the mean difference is what we're particularly interested in. Now, on the last slide, we had a sample. Okay, and this is a sample of 10. Now, we don't really know how many offices there are, so we're just going to take it as a sample and a population, a very simple case. What we're interested in here is the average difference, and we will quite often we write that as d bar. Okay, so we're going to compute that in a short while, but the average difference d bar is the from the sample. The sample difference or sample mean is d bar, and that is going to be an estimate for mu d. Now mu d is the population mean of all case-wise differences. Uh, all differences. Okay, mu d. And it is estimated by d bar. Okay, later on. So anyway, this is our null hypothesis and alternative hypothesis. Under the null hypothesis, we're going to assume we'll state the case that there is no difference on average between using UPX and INTEX. The alternative hypothesis is that there is a difference and that the average difference is not equal to 0. So this statement here says there is a difference. This statement here, just to be clear about this, that says difference is 0, which is to say no difference. Whoops. Remember that. Start there again. So that is to say no difference. Okay. So there we have there. Let mean mu d be the mean for the difference values for the two delivery services for the population of district offices. Okay, so the sample of 10 is used to represent that. Okay, now what we're going to do is move on, specify the level of significance, alpha equals 0.05. Now, what we're going to go and do is compute the average of the sample mean of case-wise differences, d bar here. So sample mean. And what we're going to do is sum up all of the values and divide by 10. So I have it done out here. The average value works out to be, the average of the case-wise differences works out to be 2.7. But I'm just going to flick back here for a second. So what I'm going to do here is add all of these numbers up. 7, 6, 4, 1, 2, and so on. And I should get a total sum of 27. Now just remember that the difference, or there's 10 values, so I'm going to divide that by 10. And then I get 2.7. So that's the average of the differences, 2.7. Okay. We also have to compute the standard deviation of the differences. So this is a calculation that you should be familiar with when working with from earlier parts of the course, how to compute the standard deviation of a set of values. We have the mean, and so all we have to do is compute the standard deviation for each set of values. So it's essentially I'll do it down the bottom here. 7 minus 2.7 squared plus 6 minus 2.7 squared, and so on. Add all of those values up and divide by n minus 1. Just essentially you divide by 9 at the end. You would get, and then you get the square root of that. And so you get a 76.1 divided by 9, get the square root of that, and you get 2.9. So the standard deviation there is 2.9. Again, I don't really have time to sort of go through the standard deviations, how to compute the standard deviations. It's very simple. It's just exactly like you've probably done earlier on in the course. So now what we're going to do is compute the test statistic. Now, this here is the same approach as you would take with a one sample hypothesis test. It's the standard error is this part here, and it's simply the standard deviation divided by the square root of the sample size. The point estimate is the sample mean, and it is 2.7. Now, under the null hypothesis, we expect a difference of 0. So, under the null hypothesis, essentially, in short, given a nickname, we'll call that the null value. The null value is 0. So 2.7 minus 0 divided by the standard deviation divided by the square root of n is 2.9 divided by the square root of 10. So that's a bit of calculator work there. So it's 2.94 is the value. So Moving on from that. Determine the critical value and the rejection rule. So alpha equals 0.05. Degrees of freedom. Remember, we are dealing with a small sample, so this is the student t-distribution that we will work with. Remember, n is 10. That's a small sample. That's an important matter. So we don't use the standard normal distribution. We don't use the Z distribution. We use the T distribution for small samples. Here the sample size is n. So the degrees of freedom is n minus 1, and that's equal to 9. Okay. Now, I'm not going to go too much more into one more thing. It is a two-tailed procedure. It's a two-tailed test. Okay, so I'll just go back here a second and let's look at where we found that. Looking at this here, mu d is not equal to 0. That indicates the fact that it's a not equal to sign there. That means it is two-tailed. Okay. So we find our test statistic, or sorry, our critical value. We find that to be 2.262, and we reject the null hypothesis if the test statistic is greater than or equal to 2.262. Now, because the test statistic was 2.94, we reject the null hypothesis. And we are at least 95% confident that there is a difference in mean delivery times between the two services. Essentially, what we can sort of say now is UPX is not as fast as Intex, and we can say that with at least 95% confidence. 5% level of significance. That is what we can say. And that ends this presentation. Or this part of the presentation. I'm going to do paired. I'm going to do proportions in the next part, part 4.